Hi, welcome to our talk. I'm Lu. I'm from the Robinhood Markets. I'm in the container orchestration team as a senior software engineer.
Hello, my name is Madhu. I'm also in the same team as Lu. I'm a software engineer on the container orchestration team at Robinhood Markets. Our team is responsible for building, offering, and operating the compute platform for all of Robinhood. And our compute platform of choice today at the company is Kubernetes. In this talk, we'll walk you through how we adopted Cilium in one of our environments, the challenges that we ran into, and the lessons we learned from the challenges and how we adapted, and then how we now live happily ever after with Cilium in that environment. Next slide, please. So before we get into any of the details, I want to clarify or explain what near production means here. Like pretty much every other company, we have multiple environments. There is a production environment as an actual production environment where all our user-facing production traffic is served, as in all the production services are run. And then we have a bunch of other environments, but there is this one specific environment where we run integration tests and personal development namespaces for the products at the company. We call it as near production because this environment is treated at the same level of seriousness and has the same response SLO, SLAs as production because it's critical for the entire company's engineering and development. If this environment stops working, the entire development at the company halts. So if there is an incident, we take it as at the same level of seriousness as a production environment. The only reason why we might prioritize it lower is if we are also simultaneously having a production incident at the time, although that has almost never happened since I joined Robinhood. With that context, I also want to explain how this environment is different from the production environment. Because of the nature of the workloads that we run in this environment, which are integration tests, right? For most part, integration tests are set up, infrastructure is brought up for them, as in the pods are kicked off for them. Data is set up for the integration tests. The tests are run, and towards the end, everything is completely toned down, including the namespace that was brought up for that particular integration test run. So because of this nature, it's a very high churn environment. And the challenges that we face in this environment is different from all other environments. Next slide, please. So what exactly is high churn? Before we even get there, let's look at some of the SLO prerequisites Kubernetes upstream projects define. So if you go look at the SLO definition page, as in the SLO MD for 6 scalability on one of the Kubernetes 6 scalability repositories, you will see these two specific lines there, which is on the left here on the slide. The prerequisites state that for any of the SLOs to be applicable, the Kubernetes cluster should be available and serving, which makes sense. And then the second prerequisite talks about the cluster churn that is considered to be a prerequisite. Before looking at the number, let's look at what the definition of churn is. Kubernetes upstream defines churn as number of pod spec creations, updates, and deletions per second, plus the number of requests that users make to the system in a given second. And Kubernetes requires this churn to be lower than 20 for SLOs to be applicable. Now, if you turn right and look at the graph that we are sharing here, you will see the churn patterns for one of the clusters that we have here in the environment over a typical 30-day period. You can also clearly see or say which of these days are work days and which days are not work days, because we told you that this is used for integration testing and personal development, right? So we expect traffic to be higher on work days. So you will see 5 peaks followed by troughs for a couple of days, and then 5 peaks, which follows the pattern of 5 work days and then 2 weekend days. You clearly see that on work days, the peaks are typically over 30, many times over 40, and it peaks almost as high as 70 pod creations and deletions per second. And in this graph, we are not even considering the user originated requests, right? These are just pod spec creations and deletions. So this is the level of churn one cluster in this environment goes through. Next slide, please. So given all these things, what exactly motivated us to adopt Cilium, especially overlay-based networking in this environment? So before we even get there, let's look at what we had in this environment before we adopted Cilium. So to begin with, we have AWS CNI as our CNI plugin running in all the environments, or that was the case before we adopted Cilium in this environment. The Cilium, the CNI plugin allows for a flat networking model that we use in all the other environments, or in all the that we used to use in this environment, including all other environments, because in many other environments, we need cross-cluster networking, so it makes sense. But in this particular environment, the traffic is mostly isolated within the namespaces, so cross-cluster networking is not required. Like even within the cluster, the networking across namespaces is mostly not required for most cases. So overlay networking works fine for this model or for this environment. In addition to that, the CNI model with flat networking works well for stable production environments, but has limitations on more bursty environments, where we need higher pod density and have very high churn, like this particular environment. So to go further, go a little bit further, the number of pods per node for us is limited in the flat networking AWS CNI model, because of the limitations that EC2 imposes on the number of secondary ENIs that you can attach to EC2 instances and the IPs that you can attach to the ENIs. Because we can't go over that number, it leads to very low CPU and memory utilization, because the pods that we spin up here are for integration tests, so they don't have high utilization. And because the utilization is so low and we cannot pack more densely, it leads to very poor cost efficiency model. So we were evaluating various solutions, and we wanted to adopt a solution that allowed us to get higher pod density. And we knew that we wanted to adopt overlay networking for that. And then we looked at various solutions, and we wanted to make sure that we did not significantly sacrifice the performance by going to the overlay model. Although this is integration test, performance is still important in this environment. So not sacrificing performance was an important goal here. We looked at eBPF, and it looked like a very strong candidate. And the moment we knew that we wanted to use eBPF, the solution of choice was Cilium, because this was the most adopted solution that was available out there. Next slide, please. So with that, how did our migration actually look like? We started from Cilium 175, and then we quickly adopted, or we quickly had to jump to a much more modern version or a much more newer version of Cilium. So we went through 3 version bumps. The way we did this was, we initially brought up a new cluster. We decided that doing this kind of upgrade or change in place was not viable. So we brought up a new cluster for personal development and another new cluster for integration tests with Cilium overlay networking model. And then we ran a lot of load tests against these clusters. And once we reached a stage where we felt confident about the knobs that we had to tune and everything, we started cutting over workloads onto these new clusters. Interestingly, though, personal development namespaces were more or less fine, but in integration test environment, because of the high churn, we ran into a number of challenges that we were not expecting. It caused a few incidents, or quite a few incidents. The term that we use here at Robinhood, like many other companies in the industry is serves. So we ran into a number of serves and we had to go back and forth between our old clusters that used flat networking model and the new clusters that used overlay networking model with Cilium. Eventually, we were able to migrate all the workloads onto the Cilium clusters. Next slide, please. Overall, if I were to talk about the efficiency that we have achieved, because we have adopted Cilium with overlay networking, at the end, we were able to pack at least 2x more pods than we were able to pack in the flat networking model. In the flat networking model, we used to set our number of pods per node, the pod density per node, to 110, which is what Kubernetes generally recommends. When we adopted Cilium, we went all the way up to 250, but it caused a number of issues. So we slowly dialed it back down to 180. Although the number was previously set to 110, we never actually hit the number 110. Our utilization or density was more around 90 to 100. Now we are comfortably able to reach 180. So we have doubled the pod density of our clusters. With that, I'll hand off to Lou to talk about the more specific challenges that we ran into. Lou, take it away.
Thanks, Madhu. So as Madhu mentioned, this migration came with a few surprises. So for example, it revealed several previously hidden bottlenecks because some other factors became new bottlenecks with much higher pod density on each node, such as the excessive API server requests, the CPU memory and month exhaustion on the node, and imbalanced workload distribution made things even worse. We also encountered a few Cilium stability issues. Although version bumps of Cilium fixed most of them, it was kind of costly and tricky to root causing and fix. The Cilium's throttling and timeouts in the high churn environments is also a challenge, and we had to build custom schedule extensions to work around it. So in the following presentation, we will select a few interesting stories to share in more details. So let's take a look at the new bottlenecks first, which is actually the first few surprises we got. With the abundance of IP addresses, we decided to consolidate two integration test clusters into one to achieve better cost efficiency. And in the meanwhile, the kubelet on each node became much busier with more pods packed onto each node. As a result, the API server got overloaded and couldn't keep up. As a result, we couldn't bring up new pods, new namespaces, and essentially it means the integration test environment got broken. And we had to migrate to the previous clusters. For the mitigation and fix, we spun up another Cilium-based cluster for the integration test environment. On one side, it relieved the API server by reducing half of the pressure, and on the other side, we got more resiliency and redundancy. We also moved from the deployment spec to pod spec for integration test namespaces, because essentially those deployment spec were the single pod deployment. And we didn't really need the auto reconciliation feature of deployment for the integration test. So it further reduced the API server pressure. Last but not least, we routed requests from the kube controller manager to the network load balancer instead of to the local API server. We removed the stickiness, and thus the request became more evenly distributed across the API servers instead of concentrating on the one which co-locates with the leader controller. Thus prevented the hottest API server get crashed. Another bottleneck is the data plane node resource exhaustion. the nodes of the new Cilium cluster somehow became more likely to encounter resource exhaustion, such as running out of CPU or memory resources, or has too many mounts. Pods on such nodes were stuck at creating or terminating. To make things worse, those nodes will be churned, and pods on those nodes will have to be rescheduled to the existing nodes, as new nodes have to go through the initialization warm-up phase before joining the cluster. And the migration of the pods on those churned nodes into the existing nodes just makes things worse because it put more pressure on some of the already kind of overloaded nodes. Thus, more nodes will be too hot and turns bad, which is essentially a cascading effect. As a mitigation, we initially tried the Kubernetes system resource reservation, basically reserved the system resource for Kubernetes daemons and system daemons. However, it turned out that it wasn't a one-size-fits-all solution. It has some own implementation limitations. And as Madhu mentioned earlier, the way we use the Kubernetes cluster exceeded the prerequisite for SLOs. So it also makes sense that the simple resource reservation couldn't solve the entire problem, although it helped a lot. Thus, in addition, we audited the applications, especially for those heavily used applications in the integration test environment. We right-sized the resource request and limits parameters, because in some cases, those requests grows with time, and eventually it is way beyond the actual usage is way beyond the request, causing the cluster to be much overcommitted, and as a result, it is easy to get burned out. In addition, we also made some performance optimizations for those applications on the cluster to reduce the resource overcommitment problem. In addition, we also made the scheduler tuning and added some scheduler extension plugins to target for more evenly distribution of the workloads across the cluster. If you turn to the left, the above two graph shows the CPU and the memory usage across the nodes on a typical day before we had any of those optimizations. And the bottom two are the newer distributions with the both tuning and plugin of the scheduler extension. As you can see, the workload distribution for both CPU and memory are much more evenly compared with before. Thus, we will have less too hot nodes, and much fewer nodes will encounter the resource exhaustion problem. Switch to another topic, which is the Cilium stability issues we encountered. One of the most costly Cilium bug we encountered was the Cilium identity collection bug. When we were running the version 1.11.6, that bug caused the exhaustion of the Cilium identities. Thus, we couldn't bring up new pods and blocked all integration tests. What happened was essentially the garbage collection was not functioning as expected. Thus, none of the spare Cilium identities could be removed to make space for the new ones. And once it reaches the max count, no new pods could be created. And what's tricky is that the problem only started to manifest almost 1 month after the initial deployment of this version. On the other side, for the personal development, fortunately, because the churn is much lower and it uses much fewer Cilium identities, so even though the same bug was there, the identities wasn't garbage collected, it was not impacted. In fact, it still have a few months or even years of headroom before the personal development cluster got hit by the same behavior. So what are the lessons from encountering this bug. First of all, if we could understand the key components of Cilium better and deep dived into how it operates when we're adopting Cilium, it will save us a lot of time to identify the problem and fix the bug, or just a version update to the newer Cilium. Also, it will be important to properly set up the monitoring and alerts, which could help us to catch the problem earlier before it actually starts to impact the near production environment. Cilium provides a lot of great metrics out of the box. However, it's kind of overwhelming in the beginning and hard to understand which ones are the real important ones. Thus, we didn't have the alert for the Cilium identity counts. And coincidentally, with the change, there was a rename of the metrics, which removed the total postfix from the matrix name. And we didn't notice the change log during that version update to 1.11.6. As a result, when the issue occurred, when we looked at the GC entries dashboard, it was empty. That adds more difficult to identify the problem. And the graph to the left actually showed how slowly the amount of Cilium identities accumulated over the month period of time, and eventually kind of reached the limit and it began to hit us. Another problem we encountered was the egress broken on some nodes, and it only happened on a few non-deterministic nodes when we scale up, and could always be mitigated by a Cilium agent restart. So it was a mystery for us. We did file an issue to the Cilium community, and we got the suggestion to update to the latest Cilium version. In the meanwhile, as a mitigation, we implemented auto-calling for when the problem occurs on the node as a stopgap. And interestingly, with the Kubernetes version update from 1.15 to 1.18, even though before we actually update the Cilium version, the problem no longer shows up. And to be honest, the exact reason is still TBD. One issue that still bothers us is the Cilium throttling and timeouts. It still kind of happens from time to time, although much infrequent now. What we see would be the rate limit error that in the logs, we will see a lot of 429s with signature like put endpoint ID too many requests. So we kind of understand it was due to the rate limit. Thus, we initially tuned the adaptive rate limiter. After that, we indeed see much less 429 errors. However, it was discovered that they essentially turned into the Cilium API client timeout exceeded error, which is even worse because that clearly indicates Cilium couldn't handle the burst of request. So even though it can self-heal slowly, but it still causes test failures. Especially, it's difficult for Cilium to keep up during the pod creation, and the IP addresses will not be assigned timely, causing the pods not healthy before test timeout. So as the mitigation, we had to introduce a new module, the burst control in the customer schedule extension to avoid scheduling too many pods on the nodes at once. To conclude our talk, here is some of our key takeaways. First, Cilium is a great technology that we love a lot. We achieved a much higher cost efficiency, and eBPF opens doors for a lot of great possibilities, like the observability, security stuff. However, just solving the networking problem won't be the golden ticket. To operate Cilium at scale, it's not sufficient to just adopt it. We really need to have a good understanding of Cilium under the hood, specifically how it operates and set up monitoring and alerts appropriately. So that's about our presentation. Thank you for the time to coming to our presentation and appreciate your interest in this topic.